All right, can everyone see my screen?
Yep.
Yes.
All right, go ahead,
All right.
Andrew.
Great. So hello, everyone. We're Team 9, Risk 5 Partition Linking and Loading on Programmable Logic Devices. I'm Andrew. We have Andrew, Matthew, Mark, and our advisor is Professor DeHaan. So before we dive into the actual project, we want to go over a little bit of background that's going to make it easier to understand where we're coming from, how it's relevant today, and what we're doing. Our basic problem is speeding up FPGA compile times. And let's see a little bit of background, how that becomes relevant. Over the past 30 years, we've seen this phenomenon, Moore's Law, where if you have a CPU, CPUs have become rapidly more efficient and performant as time has gone on. So if I'm writing some application code, I can write it for a CPU. It'll work, and I'll know that next year I can buy a new CPU, it'll run faster, and the next year I can buy a new CPU and it'll run even faster. However, over time, particularly recently, that effect has slowed down, and we've looked to other ways for increasing computation performance, such as multiple cores, and we've seen things like GPUs where you have a huge number of cores all working on the same computation. However, even that has slowed down, so we've looked towards another way to speed up computation, and that's going to be application-specific accelerators. You have, rather than writing code for a CPU, we're going to have a circuit that specifically and particularly implements the computation you want. We can go to the next slide. So one way to do that is to actually design a circuit that implements your computation, a application-specific integrated circuit, an ASIC, but that can cost millions of dollars and takes many months. So that's where FPGAs come in, and often they are a better solution. You can, instead of designing a custom circuit by hand, you write code. You write code that you compile to a physical circuit, i.e., your FPGA is able to reconfigure itself based on your code description and put together the logic gates, connections, memory, and I/O to implement your computation. And it's important to note that FPGAs aren't just a prototyping tool for if you eventually wanted to design an ASIC, but actually FPGAs are used as first-class citizens in a modern data center, and they can sometimes be more efficient than a completely customized C. So now, stepping aside for a second, we also want to, from FPGAs, we also want to look at ISAs, the instruction set architectures. When you do write code for a CPU and you compile that, you're compiling your code for a very specific set of instructions that your CPU knows how to implement. So the ISA is that interface between software and hardware. And some common ones are x86, ARM, and also RISC-V. And RISC-V is what we're going to be using in the CPUs we have in our project, because it's open source, it's free, and there's a strong tool chain backing it. And we can go to the next slide. And finally, we want to look at why mapping designs to FPGAs is hard, going back to what is our problem, speeding up FPGA compile times. When you compile code to software, to a CPU, like I said before, you're compiling it to an ISA, i.e. to a very specific set of instructions, so it's by default limited. However, when you're compiling to an FPGA, you're literally describing how the hardware works how the hardware is connected on your FPGA. So you, or rather your compiler, needs to not only decide how your code converts to the logic, but how to physically place it on the FPGA and how to route all the interconnect together, which is a lot harder than compiling to an ISA. And this problem is exacerbated because our FPGAs are large and they continue to get larger and larger every year.
So the problem that we're going up against, as Andrew mentioned, is that FPGAs and the designs mapped to them continue to increase in size. This stops hardware designers from being able to develop hardware like we're used to for software. We're unable to rapidly iterate through designs to debug, and we're forced to always recompile the entire program instead of what was changed. And FPGA compile times are currently really long and on a magnitude of hours to days, which discourages innovation and limits the exploration space for accelerated solutions. So what we have done is building off previous work that has decomposed hardware design to separate pieces, which allows the compile to happen in parallel, incrementally, then linked together. We've added tooling to automatically generate RISC-V software and firmware, and this allows a fast compiling step between unified software and hardware. And And these RISC-V cores will be drop-in replacements for the hardware component and provide standardized streaming interface, and allows us to optimize one operator at a time while always having a working version. So there's a diagram to show on the left the current monolithic compile, where it just goes for one optimized compile, and against our current smallest benchmark, it takes about 40 minutes to complete a compile. And on the right side, we have the previous work, which uses packet switch network and custom logic, and is able to compile in about 6 minutes.
All right, now I'm going to quickly switch the screen share over to our terminal, and I'm going to start a build for the previous work on the right, and we'll continue explaining this later. But basically, I can type a make command on Google Cloud, and this will start running the separate parallel compilation on the right, and we'll get back to this later.
Next slide. So this is our work, which looks a lot like the previous, but we added in the RISC-V drop-in replacements. And then we also replaced the controller to be software, which allows it to support a wider array of FPGAs, including those that don't have an ARM core on it. And we're expecting that the compile time to be about 2 seconds, which is a lot quicker than 6 minutes, and definitely a lot quicker than a current monolithic compile of 40 minutes. Next slide. So coarse grain alternatives that are currently available. You can compile high-level synthesis code to harden ARM core. And the approach to this provides better single-threaded performance than soft cores, but usually is limited to 2 to 4 cores. And it complicates the evaluation of highly parallel programs, such as those that are usually run on FPGAs, and leads to latency between operators, memory systems, and physical location that differ from your final design, hardware design. There's also a registered transfer level simulation, which simulates the low-level logic that will be mapped to the FPGA. And it's well supported in very current commercial and open source tools, but it takes several minutes to compile and can only be run with very small test inputs, given its extremely low input. And compared to current monolithic compile, it's very slow, 400,000 times slower than hardware for rendering, and takes about 6 minutes.
So some specifications that we were under when making this project is that the leaf cores need to be a drop-in replacement for the hardware block leaves and need to be able to interface with a network via streams. Additionally, they should be under 2000 LUTs and use fewer than 10 VRAMs in order to fit within our design. The controller core need to be able to coordinate data flow through the network and leaves and be able to set up direct memory access for DRAM control to move data through the BFT. At the end of the project, we need to be able to quantify the results with the Rosetta high-level synthesis benchmark suite, and our goal was to achieve compile times of under 5 seconds. Additionally, we wanted to be able to write code once and use the same code for hardware on the FPGA and for software on our RISC-V CPUs. And we were finally hoping to be able to use fully open source components for our project. Our business model is that we didn't really have one. We're intending to release this as fully open source, which is why we're building off of fully open source components. Our intention is to be able to allow users to download and use our product for free. There aren't too many ethical issues. As it is open source software, it's distributed without a license. And while it could be used in applications such as life-critical devices, the end user who creates such life-critical devices is responsible for verifying the correctness of their design, even if they do use our toolchain to help them get there.
Yeah, so some engineering standards that we're using as part of our design. So the most important one here is this AXI4 stream bus, which is an industry standard that allows us to create these components that we can place into our design and exchange them on the fly. And so this is, in the diagram on the right, you can see at the top right, the AXI stream is what connects to our user logic. And it allows us to take our RISC-V cores and have them be drop-in replacements for some of the other hardware logic. So talking about our controller implementation, so this is what's allowing us to use our system on a wider range of FPGAs that don't have hardened ARM cores on them. And so this is all soft logic that's fully open source. It's implemented with MyGen HDL and uses these open source LightX components. We use a VEX RISC-V core, and sort of this allows us to set up and coordinate data flow between all of the user logic. And this is something that we can distribute as part of our full system.
So the leafs are implemented using a modified VEX RISC-V as a soft core replacement for the hardware leaves. We use VEX RISC-V core. We modified it to be able to run custom streaming instructions, which allows our core to communicate with the BFT. We, using our core, send and receive data over the packet switch network, and we do this via an AXI stream interface. We pair our modified core with a customized GCC RISC-V toolchain, which allows us to generate object files with custom streaming instructions. The two custom instructions that we created for this project are stream write, which allows us to write a value into a stream, and stream read, which allows us to read the next value from that stream. So some design choices that we made when building this project were that we used the VEX RISC-V as our soft core over some other RISC-V implementations. This is because VEX RISC-V offers extremely high performance and is optimized for the FPGA. One good comparison to make is with the Pico RV32, which has its merits and is widely used, like the VEX RISC-V, but has 4 times slower performance. Additionally, the VEX RISC-V is built using a plugin system, which makes it very easy to modify. And this was extremely necessary for us in order to be able to run our custom streaming instructions. We use the custom streaming instructions because the leaf cores need to be able to communicate with the leaf interface through streams. And an alternative to using stream instructions was accessing streams through memory mapped operations. This would have been easier to implement than the custom instructions. However, the end result would have been about 30 times slower due to repeated memory accesses and potential stalls.
So some status of our project at this point. So this controller implementation that we've described, it is fully working and is fully integrated with previous work. So we can now allow this previous work to be used on a much wider range of FPGAs, sort of including the one that we've chosen. And we can perform this separate compilation, and we can generate full partial bit streams that we can upload separately to the board. And this allows us to only modify a single operator in our graph and get this separate compilation and linking. On our Leaf soft cores, we were hoping that we were going to have this fully working at this point, but unfortunately it's not 100% done, although we're confident it'll be done before the final report. So our stream instructions work. So we have these custom instructions. We're able to read and write from AXI streams reliably. Our problem is we were trying to upload the actual instructions that would be stored on that Leaf soft core over the network, but that uses way too many resources for our requirements. And so we're going to sort of replace that system with some other work that will be done in the future. So that's the end of that. All right, now we're going to switch over back to our terminal. So I downloaded those. I downloaded the results of that compile, so that that compile finished, and that is obviously faster than sort of the 40-minute compile, but it's still on the order of several minutes. And to sort of demonstrate that this works, we're going to we're going to download our program to the device. So this will load our controller and load the different operators. And then we can program the device and show the actual result. So here you can see it uploading uploading and linking together all of our design components. And we can also generate sort of the configuration that's required for this design automatically. And then we can program our device. So here you can see I have a serial connection to the device. And we can go ahead and reboot to load our custom firmware, which this is a custom accelerator designed to render a 3D image into 2D. And we can sort of show that here that this is a 3D model of a bunny that we have rendered onto our terminal. And so, that took several minutes still. And even though we don't have our leaf cores 100% working, our compile flow is done for them. So we're able to sort of demonstrate this compile, and you'll be able to see it is very fast. So we can start our compile. And, oh, okay. First, let me show you how we actually change this to run on software. So we have sort of a definition here that you can see the, right now this page is being mapped to hardware, and we can change this to say that we're gonna map it to software. And it fully compiled all 6 of our operators in that time. So that is actually how long it will take in the final system to compile. This is the final code. We just have to finalize our hardware implementation. All right, any questions?